Hello everyone. So in the previous class we discussed certain results on Lebesgue integral and Lebesgue measurable functions. Now today we'll continue the discussion. Let us recall about Riemann integral. Suppose f is a bounded real valued function defined on the closed interval a comma b, and if there is a partition of closed interval a comma b into n parts, that is x0, x1, etc. up to x2, x2, etc. up to xn. Now for each partition we know that we can find S, which is summation I from 1 to n mi into xi minus 1, where this is length of the interval and this is the supremum of f of x in the ith interval. This is upper Riemann sum, and the lower Riemann sum, which is given by small s, which is summation I from 1 to n mi into xi minus 1, where this mi is the infimum of f of x in the ith interval, that is xi minus 1 to xi. We knew all these results. Now let us define the upper Riemann integral. We know that upper Riemann integral of f is nothing but infimum of s, where this s is taken over all partitions of closed interval a comma b. Similarly, we can define lower Riemann integral of f by this symbol, where this is taken over supremum of s for all partitions of closed interval a comma b. Now we knew that the lower Riemann integral is always less than or equal to upper Riemann integral, and in fact these two are equal to each other provided if it is integrable, that is f is Riemann integrable over closed interval a comma b, and the common value is denoted by r integral a to b f of x dx. Why we are writing? Because just to differentiate this one from Lebesgue integral, because we are going to discuss about these two, Riemann integral and Lebesgue integral later. By a step function, we mean a function psi where psi of x takes the value ci whenever your x lies in between xi minus 1 and xi. Where this is a partition of closed interval a comma b. And if psi is a step function, then we have proved this result that integral a to b psi of x dx equal to summation I from 1 to n ci into xi minus 1. This we have discussed in the second semester class. And note that our upper Riemann integral is nothing but infimum of integral a to b psi of x dx. These two are equal to each other for all step functions whenever psi of x is greater than or equal to f of x. So whenever your psi of x is greater than or equal to f of x, see, you should note that the integral a to b psi of x dx will be greater than or equal to integral a to b f of x dx, and you are taking infimum of this. So obviously this has to be equal to the upper Riemann integral. Similarly, lower Riemann integral is nothing but supremum of integral a to b phi of x dx, where your phi of x is less than or equal to f of x. Because if you take integral a to b phi of x dx is less than or equal to integral a to b f of x dx. You should note that our upper Riemann integral and lower Riemann integral satisfies the condition r integral a bar to b f of x dx is less than or equal to integral a to b f of x dx, which is less than or equal to integral a to b bar f of x dx. And since integral a to b phi of x dx is less than or equal to integral a to b f of x dx, your lower Riemann integral must be equal to supremum of this, so that this condition gives you the answer. Now, given problems on Riemann integral, you just work it out and write it as an assignment. Next, the Lebesgue integral of a bounded function over a set of finite measure. We have discussed what is meant by characteristic function. We say chi is a characteristic function of E whenever chi of x takes the value 1 if x is in E and 0 if x is not in E. And we have defined a simple function. What is meant by a simple function? A simple function is the one if it is measurable and assumes only finite number of values. So if phi is simple and it takes finitely many values, then we have defined phi can be written as summation I from 1 to n ai into chi ai, where ai equal to this. I've explained this one in the previous class. And this representation is called as canonical representation of phi. Now definition, if phi is a simple function which vanish outside a set of finite measure. So this can take only finite measure. It will become 0 if you take outside a set of finite measure. So we define the Lebesgue integral phi by integral phi of x dx is nothing but summation I from 1 to n ai into measure of ei, where phi has the canonical representation of this form. So remember, if phi is a simple function which vanishes outside a set of finite measure, then the Lebesgue integral of phi is given by this, when phi has the canonical representation of this form. We sometimes abbreviate the expression of this integral to be simply integral phi. Instead of writing phi of x dx, simply we write integral phi. That means it is integral phi of x into dx. If E is any measurable set, we define the Lebesgue integral of phi over E is Lebesgue integral phi chi E. It is often convenient to use this representation, which is not canonical in general. And the following lemma is very useful in that. If phi has a canonical representation of this form, where ei is a disjoint and measurable sets of finite measure, then the Lebesgue integral of phi is summation I from 1 to n ei into measure of ei. See, just now we defined the same thing. So this is very easy to prove. You just prove the lemma and write it in assignment. Now proposition, if phi and psi are simple functions which vanish outside a set of finite measure, then prove that integral of a phi plus b psi is a integral phi plus b psi if phi is greater than or equal to psi almost everywhere, then integral phi is greater than or equal to integral psi. Let us prove this one first. What they are given phi and psi are simple functions which vanish outside a set of finite measure. We knew the definition of simple functions. By the simple function definition, we can write this one in the canonical representation form. So let us write this in the canonical representation form like this. For this, let us assume there exist two sets ei and bj with the sets which occur in the canonical representation of phi and psi. Then the sets ek are obtained by taking the intersections ei and bj to form a finite disjoint collection of measurable sets, and we write phi in the canonical representation k from 1 to n ak chi ek, and psi is summation k from 1 to n bk chi ek. And so that a phi plus b psi is nothing but a into this plus b into this. Take the common factors and the summation, you'll get summation k from 1 to n aak plus bbk into chi ek. But by the definition of Lebesgue integral, see, we have defined this. So by this definition, the integral of a phi plus b psi is equal to summation k from 1 to n aak plus bbk into measure of this ek. But if you split this one into two, we'll get this, where this is nothing but integral of phi plus this is nothing but integral of psi. So we have proved the first part. Now let's prove the second part. To prove this, first you should recall this result. If phi is greater than or equal to 0 almost everywhere, that means wherever this result fails, for such collection of points, the measure is 0. Now, the measure of set of all x where this result is failing, that is, phi of x is less than 0 means it is not greater than or equal to 0. For such sets, measure should be 0. Hence, by the definition of Lebesgue integral of phi, we knew that If this is greater than or equal to 0, then the integral is also greater than or equal to 0. And let us prove this argument. They are given phi is greater than or equal to psi almost everywhere. Now if you send this one to this side, phi minus psi is greater than or equal to 0 almost everywhere. But by this result, then integral phi minus psi must be greater than or equal to 0. But that implies that just by the above property, integral a phi plus b psi, take a as 1 and b as minus 1. We can write like this. So that is nothing but integral phi minus integral psi is greater than or equal to 0. And if you send this one to this side, that will give you integral phi is this should be greater than or equal to integral psi. This completes the proof. Thank you.